Thanks, Jenya, for this wonderful presentation. So we will continue now with an extended Q&A, our fire chat to discuss the reliability side of bifacial solar and trackers as the key components in utility scale solar. So I would like to start it this way, that regarding reliability, when you would have to name the 3 to 5 key characteristics of bifacial solar, what would that be?
Yeah, thanks again for having me. So from a reliability perspective, the bifacial modules do present some differences relative to their monofacial counterparts. So of course, the back surface of the cell does not have complete coverage and metallization. And so there are some differences there. The back surface of the cell has different treatment, and so it has some different sensitivity to it. That, I think, was well highlighted by the PID case study, where when the back surface is left exposed to collect static charge buildup, it does have a fairly measurable, substantial, and consistent aging behavior that is different from the front side. So in the field, the way we would see this is basically a degrading bifaciality factor, which nobody is factoring into their energy models today. Of course, that's not the only difference. Most bifacial modules tend to be glass-glass because of the large size of new modules and because of the weight considerations. These are typically 2 millimeter glass. 2.0 millimeter is the most common thing we see today. 2.0 on the front, 2.0 on the back. When glass is so thin, it cannot be tempered. It can only be heat treated. So we have seen an increase in failures in mechanical testing. This is caused both by the increased size and by the thinner glass. We see when performing static mechanical load testing, we see an increased number of failures from the glass popping out of the frame, from the glass breaking, from just catastrophic kind of failures. This we see more nowadays than we used to with the smaller module size and the thicker module glass. I think those are probably the big points I'll make. There are definitely differences in how you optimize the design for energy production, of course, as well, which relates to tracker compatibility. But yeah, from the reliability side, I think I'll leave it there for now.
Okay, cool. And then when you look at trackers, so what will you see there as the key features regarding reliability? Also had to.
Yeah, so there have been a number of failures in the field that I've heard about caused by over torquing the module clamps. So that's not really a product design issue and more of a implementation issue. If the new bifacial modules with thin glass and large size, when they're over torqued, the glass was popping out of the frame in the field. In several utility scale projects, I've heard of that. But okay, that's a user error. So let's put that aside from now. For the biggest impact, I think, is on the performance aspects. So the backside shading factor has a fairly is primarily driven by tracker design considerations. So all of the things underneath the module are basically shading light from hitting the back of the module. So the combiner boxes, the wire management, drive lines, posts, any kind of bearings underneath modules, that can contribute to non-uniform irradiance of the backside of the tracker as well. The non-uniformity can contribute to more electrical mismatch. Under operating conditions, that's probably not a substantial difference until it could cause a hotspot. This could happen. I think it's not the the hotspot issue from non-uniform backside illumination in a normal like grass cover, we don't see too often. If you have very reflective albedo, this could potentially become a consideration as well, maybe in snow-covered areas. Of course, wind plays a huge role in the durability of very large modules on trackers. We've seen a number of failures in the field from that. These modules are very large nowadays, 2,400 millimeters plus module length. We're seeing, because of the large module size, trackers now have to be taller. So at maximum rotation, you still maintain the required clearance from the bottom edge of the module to the ground. So posts have to be raised. Oftentimes when the module is longer, it's also wider. And so you have to, under maximum deflection, be careful that the center of the module does not hit the torque tube, which could happen under snow loading conditions. And if you have a glass module, that could obviously damage it. Typically, there's a junction box in the middle, and you can hit the junction box and you could shatter the back glass. So sometimes the module mounts need to be actually raised up, which definitely adds cost, or the frame needs to be made thicker to ensure that at maximum deflection, you don't have contact with the torque tube. Yeah, so there are a number of kind of nuanced considerations.
Okay. So when let's maybe look at bifacial first. So and then maybe look at the differences or the special features. I think you mentioned already glass. I found it interesting in your presentation that actually the share of modules, bifacial modules being used in the US that are actually glass backsheet, they still had a considerable share. I would have thought actually it's almost all glass, because I don't know so many manufacturers that use actually glass backsheet. So what's the reason, do you think, that people opt the one or the other? There are, of course, different fractions, different interests. Some pushing for that, the others are pushing for that. But what have you observed in your testing?
So I think there are two drivers of why we're seeing that in the US. The largest utility scale build out in the US is happening in Texas. Texas has very extreme hail. It's kind of the hail capital of the US, maybe the hail capital of the world. There have been a large number of insurance claims made because of what's called gorilla hail, or hail that's the size of a softball, shattering a bunch of panels. Typically modules with 3.2 millimeter front glass are thought of as being a bit more robust for impact, for direct impact from hail. That's different than deflection, damage caused from like snow load deflection or wind load deflection, but really a point impact from hail. 3.2 millimeter glass really has to be a glass backsheet module because it's too heavy if you use a second piece of glass on the back. And Texas is just such a large market, it skews now the entire industry. What Texas does kind of makes the whole, is what the industry does. The second consideration is Jinko. Jinko is either the largest or the top 2 or 3 suppliers in the US, and they're pretty dedicated to glass backsheet module construction. So, just like Texas is so big that what they do, the industry kind of skews the industry statistics, Jinko is also so big that what they do skews the industry statistics. So the number of module types, I think, are mostly glass. The number of megawatts, there is still a lot of glass backsheet in the US. Okay.
But in general, you, as you said, I think in the ITR PV, we can also see that it's mostly glass modules actually that are being used when you use bifacial modules, right?
Yeah, if you do the math by the number of product types, then yes.
Okay.
Most manufacturers are doing glass.
Yeah. And what are you seeing there? We've seen obviously also modules. You've also shown that in your presentation that they are much larger than 2.5 meters now, and so long, and it's getting bigger and bigger. We have now 700 watt plus modules in the market. So what are we seeing there in terms of glass, and what does that mean for reliability?
So as size grows, thermomechanical stresses definitely are impacted. It's definitely a consideration that needs to be considered. I should say that at PVEL, we've seen the 210 millimeter wafer, very large modules, and the 182 millimeter large but slightly smaller modules. We've seen good performance from both. So just because it's very large doesn't mean it's should be avoided necessarily from a reliability perspective. Of course, if that is only if the design is good. We definitely recommend everybody look at the PVEL product qualification program test reports on a specific bill of materials before assuming a product is reliable. However, it's basically boils down to the two coalitions of wafer sizes. On the 210 millimeter side, it's mostly Trina is the big one. I think Ryzen is also there. Those are the very large modules that are 2400 by 1300 millimeter, in that range. Or the 182 millimeter wafer size, that's, Jinko, Longi, and several others are kind of leading the standardization of that product design. I think that currently has more participants and market share, the 182 millimeter designs, but those tend to be in the 550 watt range, where the 210 millimeter tend to be in the 600 plus, 650 plus or minus watt range, like you said, even getting into the 700. So I think right now the jury's out on whether or not there are impacts to installation speed. One example or one analogy maybe we can look to is 5 years ago, maybe a lot of manufacturers tried to get rid of the frame, and laminates were being shipped, and they were instructing to use mounting clips. And the construction world, the EPC world, pushed back so hard. They said, we don't want this. It's hard to handle. It's hard to install. It's slow to install. They're very fragile. You put it down on a rock in the field. It looks great on paper because a frame costs money, and you get rid of it and you save that money. But the practical considerations in the field basically killed that, and nobody's trying to do that anymore. So the EPCs are just now starting to get experience with the very, very large modules. Even though the press releases and the data sheets maybe have existed for a while, I think we're only now starting to see real volume shipments in the field. And we'll see how the pushback goes. So far, I think I'm not super confident that the very large ones will be maintained, because the construction workers maybe won't like them, but I haven't heard anything yet.
Yeah, well, yeah, will be interesting. So I just heard it's not utility scale, but in Germany, even apparently installers who do rooftop installations, they like glass now because they sort of got used to that. And so I think it's maybe, yeah, let's see. Jury's still out. If we go now to packaging or to other parts of packaging, so encapsulation, you also mentioned reliability and testing for EVA versus POE. There are also combinations, EPE, and the more EVA, the less reliable, if I understood it correctly from your charts. So what are you seeing there? I found it interesting that you showed also that that POE basically, which did not exist in 2018 and has almost now 50% market share. So will that continue actually like that, or will we see mostly then also EPE, because POE is obviously a bit more expensive than EVA, but what are you seeing, and also regarding reliability?
Yeah, so originally, folks thought that any EVA in a glass module was bad, should be avoided, because when EVA degrades, it emits acetic acid and other chemistry outgases from the polymers, and a glass module package is really hermetic. And the early glass modules in the field had pretty widespread failures. And when I say early, I mean 20 years ago, had pretty widespread delamination and failures in the field. JinkoSolar famously, very long time ago, had glass modules that had just bubbles everywhere inside after a couple of years. So the EVA was originally thought to be avoided. There has obviously been a tremendous amount of polymer physics research and material science that's gone into the development of different EVAs since then, and they've gotten quite stable with all of the additives that have been introduced, and it's a very engineered material nowadays. When we at the lab originally saw EVA and POE coming in the same package, that was originally very concerning, that you're mixing materials now. Is there going to be new considerations as these things age? But in the lab testing, we have not actually seen any real red flags, and we've seen fairly good performance from the EVA POE mixed modules. POE is typically used on the backside because it's a much better charge transport barrier, so it protects the back of the cell from PID. I should say that the POE EVA combination we said was better than the EVA combination, specifically just in the PID test. So in other tests, maybe it's comparable. It's not EVA double layer is not necessarily worse. But in the PID test, it's clear when we pulled the data apart that the modules that have EVA behind a bifacial cell have a pretty consistent and much higher degradation than ones that have POE behind it. I also think originally some of the mixing of EVA and POE into a single module was driven by, like you said, POE is slightly more expensive. And in the early days of using POE, there was not enough manufacturing capacity to support the industry. And so the availability of POE was also difficult. Today, as you said, more than 50% of the modules we see have at least some POE, not necessarily on both sides, but some POE in the module. And so the manufacturing capacity, I suppose, has been scaled up. And but it's still, I think, a little more expensive. And so that'll continue driving. And so far, we haven't seen a reason to replace the front EVA with POE, because the front EVA seems to be doing okay, and the back POE seems to be doing okay as well.
Okay. Then let's maybe go to the core of the module. Then the cell. You also showed basically that PERC fully dominates, at least from what you saw in the US, and I think worldwide it's also true. But I think the N-type share was very small. I think where it's happening this year. Jinko is coming big with N-type. They also talk on this conference about that. But regarding bifacial, that will be probably one of the drivers also, because also towards maybe HJT, because the bifaciality of PERC is not outstanding, put it this way. So what are you seeing at the moment in this direction? What are the drivers also from a bifacial module point of view?
I think that as you alluded to, there has been a lot of talk of N-type over the last probably 3 years, but not a lot of action, and a lot of press releases, a lot of champion cells, a lot of R&D. It's going to take one of the big guys to really convert, and then everybody will follow. And I agree, Jinko is going big on N-type already. And I think this is the breaking of the dam that will cause the N-type flood, which is great. There is a lower temperature coefficient, which is very impactful in the US. All the sites tend to be in all the large utility scale sites anyways tend to be in fairly hot climates like Texas and Southern California, Nevada, Arizona. So the temperature coefficient plays a material substantial role. And of course the bifaciality, as you suggested. All utility scale plants are bifacial in the US. The bifaciality improvement does play a role. However, couple of things. The bifaciality of commercially shipped PERC modules fell recently when there was a PV glass shortage, and a lot of manufacturers had to shift from low iron, soda lime, high transparency PV glass to just standard glass, which had lower transparency. And so that's outside of the cell, but the back glass was less transparent than what was originally spec'd. And there's no warranty on the bifaciality. It's just a number on the data sheet, and it's got a pretty big range. It's 70 plus minus 10%. That's 60 to 80 is a very large range, and we started to see closer to 60. And that impacted economics of very large utility scale projects in a substantial way. And so that needs to be resolved as an industry to get the higher transparency PV glass back to a production level that can support all of the bifacial modules being produced. There is a lot of new PV glass capacity coming online in the coming years, so I think that should be okay. When PERC was first introduced several years ago, everybody was fairly optimistic. It was promising. ALBSF efficiencies started to plateau, and PERC really was the next step. And a lot of PERC was quickly deployed. And then we started to see new aging behaviors, which was eventually characterized as LETID. Originally, we didn't know what it was, but it seemed to be meta-stable. So degrade, it would improve. It was a more complicated cell architecture that had more complicated behaviors. Eventually, over several years, manufacturers figured out a LETID stabilization process in the cell factory that includes a high temperature current injection or a laser induced current injection at very high intensities. And today, LETID is much less of a problem.
Yeah, sorry, please.
Well, I was going to say, I don't know what the next thing is. Okay. But a new cell technology typically comes with a new experience on degradation.
But that's also what I read in your scorecard, that LID and LETID did not really play a big role this year compared to last year and the years before, right? So that's what
I think that a lot of those things have improved. We have had the interesting vantage point of being able to see different technologies mature slowly. Multi-bus bar is a great example. We have a case study in the scorecard as well, where when multi-bus bar interconnection was first introduced, we saw a wide range of thermal cycling performance, some quite bad. And then over a couple of years, 3 years or something, we kind of saw the average degradation in thermal cycling for multi-bus bar get better and better and better. And this past year, I think all of them were quite good. And so we really saw the industry implement a new technology, figure out all of the kinks in the manufacturing process and the materials over the course of a couple of years. And now it's quite mature. But of course, there are new technologies being introduced always. So you have to always, the game of policing the new technology is never over.
Yeah. So I think that I also found that interesting that you wrote that this year's thermal cycling results have been the best in PVEL's history, so that really 90% of the bombs tested degraded by less than 2%. So what's the reason? Also this general evolution, or was there some?
I think it's exactly that. It's multi-bus bar has gotten good, has developed the technology and the performance. So typically when one thing is changed in a module design, it has other impacts that are maybe less obvious that take a little while to figure out. So the multi-bus bar wire is about 350 microns thick. So it's actually quite a bit thicker than the flat bus bar wires that were used before. When you increase the thickness of the interconnect, you have to increase the encapsulant thickness accordingly. That ratio of encapsulant thickness to interconnect thickness plays a big role in thermal cycling degradation. Of course, the encapsulant thickness also costs more when it's thicker because there's more material. And I think there is an optimization there that initially wasn't appreciated by all manufacturers. So we saw thin encapsulants with thick busbar wires, and that had quite poor thermal cycling performance. That wasn't the only impact, of course, but that was one that we could point to.
And in Dampede, for example, you said that and I found that interesting that many bombs with concerning Dampede results came from manufacturers that were actually listed as top performers for other modules. So what was the reason?
So similar to thermal cycling results getting better, we actually saw damp heat results getting worse. Similar but opposite. And I think that kind of makes sense with new cell technologies. So the previous scorecard was, I think, more about engineering module designs. Everybody went to a bigger design. Everybody went to, larger design, different thermomechanical characteristics, multi-bus bar, bigger wafers, but the same cell technology. I think now we're seeing a bit of a shift in the industry back to cell efficiency optimization rather than on the module side. And a lot of the incremental improvements are happening at the cell level again. And this, of course, this N-type wave is going to be a big step in that direction. And high temperature for elevated amounts of time can cause different aging mechanisms. Boron oxygen destabilization was quite, the complexity was highlighted, and the metastability was kind of highlighted in PERC. Of course, with N-type, it's going to be something different because, now it's phosphorus instead of boron, or even the P-type has shifted to gallium. But I don't know what it will be, but I think it will be something.
Okay. Then I also found interesting, you also looked at the PAN performance. So for those who don't know what PAN is, that's the module specs in a file that can be used for modeling. So why were all the PAN top performers bifacial modules this year?
Well, yeah, that's a bit of a how the analysis is performed right now, that the PAN files are created and there's an energy model performed. And of course, the PAN bifacial modules have higher yield than monofacial modules always. But what's for sale is just the front side. So they were kind of bundled together. In the future, we might look at them separating monofacial and bifacial as two different categories. But I think at this point, it's no surprise that bifacial is, from a performance perspective, consistently greatly outperforming monofacial counterparts.
Okay, but in general, were you happy with the PAN files that were delivered, or because I think sometimes?
Well, PAN files that are presented here are all created by PVEL based on measurements performed by PVEL. So all of the PAN files are reliable and based on reality of product performance. What we have seen elsewhere is PAN files can have varying performance. I'll give you one anecdote from one of our large downstream partners. It's large utility who received 5 different pan files for the same product type from 5 different sources. Same product, nothing different about the module, same module model, but 5 different sources of pan files, and they saw the impact to their returns swing by 2.75%. So that was the impact to the LCOE. Swing from the worst pan file to the best pan file by 2.75%. That's a huge number. That's enough to make or break a project in the US. And there was nothing different about the plant design or the product or anything. It's just where you get your pan file source. So definitely people have to be quite careful in obtaining third-party PVEL pan files, which are, reliable and consistent and based on real measurements. It is getting challenging as modules are getting bigger and bigger and bigger, that the machines have to get bigger and bigger and bigger as well. So I think there's a lot of extrapolation happening right now in the industry that may not be so reliable.
Okay, so when you look at the next step, it's of course always difficult to look into this crystal balls, but regarding reliability of utility scale solar plants, and coming back to once the module and the tracker as 2 really important parts of this product. What do you see there, or what do you think are the challenges that needs to be looked at in the next 3 years or so? I think the market is really going through the roof. So we've just reached the terawatt level, and it continues very steep. So what are the challenges?
From the module perspective specifically, we've been testing modules for over a decade, and we've seen module quality follow other things like manufacturer solvency. For example, if a manufacturer sometimes is experiencing financial stress on the verge of bankruptcy, some decisions are made that may not be positive to module quality. We've seen new regions come up from 0 to a substantial manufacturing base, like we've seen in Malaysia and Vietnam and now Cambodia and Thailand and Southeast Asia in general. And even if you rewind back to 2008 in China, there was nothing there, and then everything started small and then got very big and started manual and got very automated. And now it's very, very sophisticated manufacturing. I think what we will see in the coming years is a general regionalization of a manufacturing base. So I think the whole world is getting a little bit more protectionist with their trade policy. US for sure, but also India and also Europe. And I think we're going to see more domestic manufacturing incentives. Like, India has this, US is now talking about it. It's going through Congress right now. Everybody's hopeful that something will pass. And we're going to see manufacturing really at scale in new locations where there is not a trained base of people. US does not have people that have experience operating a Tabor stringer and a manufacturing line the same way that Malaysia does, and definitely not the same way that China does. And some of the biggest quality impacts that we've seen over the years is when you have a totally untrained workforce coming into a factory to build modules. It may look easy on paper, but devil's in the details with cell and module production. And I think the regionalization of the manufacturing base is actually going to cause a dip in quality, and increased vigilance on technical qualification of suppliers from brand new factories and brand new locations will be increasingly important. On the tracker side, it's a little more complicated because they're so different. Nextracker and ATI and Soltech and FTC have different ways they fail. It's not, a module is, there may be different sizes and different details, but you can put a module in thermal cycling and what kind of stresses are going to be imparted. You can't do the same thing with a tracker. You can't put a Nextracker and a FTC into a chamber and run it and see which one lasts longer. because a lot of the failure mechanisms can be different. Dampers failing, gearboxes failing, a lot of electronics and software issues, a lot of stuck trackers, a lot of wind-related failures. I think as an industry, we're still learning about wind-related harmonics that are new things are being learned and experienced. A lot of the wind tunnel testing is performed on very small models that I don't think is capturing the full complexity of the real field situation. It's also flat, and we're seeing more and more topography. A lot of the very easy sites that are perfect giant flat rectangles in California have been built already, and we're seeing more and more challenging sites and water features and topography, like I mentioned. And so I think we will see different wind impacts on trackers. Just like everybody else in the industry, the tracker manufacturers are also being forced to cost reduce, and cost reduction for a tracker really comes down to kilograms. How much steel is being installed? And less steel means more and more sensitivity to external forces that maybe aren't extremely well understood. I shouldn't say there is a pretty good understanding of wind dynamics. It's just not complete, especially for varying tracker designs and especially for topography.
Yep, and we will see probably also trackers now coming to the northern sphere. At least they are talking about that in Europe.
Yeah. So I think I'm introducing more questions than answers, unfortunately, on the tracker side. But yeah, I don't have a good solution for how to technically qualify a tracker that is maybe different than the last one or new.
Okay, but nevertheless, I think we have.
Nevertheless, we march forward.
Yes, we do. Thanks a lot, Jenya. That was wonderful talking to you.
Thanks, Michael. Thanks, everyone.
Thanks.